Okay, consider this. Look at the doorknob that the cat is trying to manipulate. Especially pay attention to where the doorknob is relative to the hinges. Okay, it is on the opposite side of the door relative to the hinges. Of course, where it is height-wise is to be convenient for the people who use it. In addition to that, pay attention to the way the cat is now pushing with its paw on the door. Okay, this is a pictorial of the door. This is where the hinge is. This is the doorknob. I hope that you have not seen any door whose doorknob is closer to the hinge. The hinge is, the hinge and the doorknob are far apart. The doorknob is as far away from the hinge as possible. Now also, I hope that you realized when trying to open the door, the force that we exert on the hinge to pull the door open is in this direction. That's also the same direction the cat exerted with its paws when it tried to open the door. Look at that. If the cat instead tried to apply a force in this direction, that would not have opened the door. So we have two things I hope that we have noticed. To get the door to opening the door in this case meaning rotating, we had to have a doorknob as far away from the hinges as possible, and we had to apply a force that's perpendicular to the door. So what does that mean? That means if we need to get an object to rotate, it's not going to be sufficient to apply a force. It's going to be important to know where to apply the force relative to the point about which the object is going to be able to rotate. So in the case of our door, again, if I draw it again, to get the door to open easily, two things were important. Where the force is applied relative to the hinge, and how is that force applied, in what direction. Both of these were important. So it's not sufficient to just talk of a force when we try to change the state of rotation of an object. We have to talk of a force and how is it acting relative to the point or axis about which the object is going to rotate. So that quantity that does that for us, we call it torque. The symbol we use for torque is tau. And the torque is a force. It is a vector like forces, by the way. It is a vector, but its magnitude, it's a force times a distance. The distance, we call it a lever arm. The equation for torque is force times lever arm. An alternative name for lever arm is moment arm. What we define as moment arm or lever arm, it is the shortest distance separating the line of action, which means the line along which the force is acting, the line of action of the force from the pivot point, the point about which the object is going to be capable of rotating. That's important. Okay, remember, as I just mentioned, torque is a vector. If the axis of rotation does not change, for example, the hinges in a door, we will usually use the direction of rotation, clockwise or counterclockwise, for the sign of the torque. Now, let's try to explain the moment arm or the lever arm again. Let's assume I have an object here, and I have a piece of metal going through it and set like that. Now this object, we are assuming that this object can rotate about that piece of metal. To get the object to rotate, we are going to need to apply a force that's not along the line of action to get the object to rotate. We need to apply a force that results on a non-zero lever arm. Not like this force here. This force here that I have drawn, if I pull with that force, all what it is going to do is exert a force on the axis of rotation here. Now, what I have as the dashed line here is what we call the line of action. Let's consider this object here, and we drilled a hole through it and we put some kind of a pin so the object can rotate about that pin. So the pin is marked in black here. In this case, the term, that pin would be our pivot point. So to get this object to rotate, we need to apply forces. One force or more, depending on the case. For example, let's consider this force. Let's call it F1. What we define as line of action is the line along which that force is acting. I'm going to mark that in red dashed line. So all what we have to do is we draw a line parallel to that force. That's the line along which that force is acting. What we define as the lever arm is the shortest distance from that line, the dashed line, to the pivot point. So that shortest distance from the dashed line to this point here. So I'm going to draw that in blue. So that would be this distance, the perpendicular. This is what we call the lever arm. This particular force is going to result on the block rotating in the clockwise direction. Now, let's consider another force. Let's consider this force F2. I'm going to try to draw the line of action of that force as well. The line of action of that force goes through the pivot point. This means that that force is going to result on no lever arm, since it goes through the pivot point. So that force is not going to be capable of rotating the block. F1 is capable of rotating the block. So there is a torque T1 corresponding to F1. That's going to be F1 times, let's call it lever arm 1. Torque 2 is 0 because the lever arm, due to force 2, is 0. Let's consider another force. Let's consider a force acting here. Let's call it F3. In that case, my lever arm, my line of action is along this direction. So my lever arm, we draw it in blue, is going to be this much. That's lever arm 3. So my torque 3 is going to be F3 times lever arm 3. Now torque 3 is going to be capable of rotating the block in the counterclockwise direction. You think of that force by itself. How is the block going to rotate if that's the only force acting on it? And in this case, if the only force is F3, my block is going to rotate like this, counterclockwise direction. However, the torque due to F1 is going to rotate it in the clockwise direction. So these two torques have different directions or opposite directions. Summary: torque is the rotational equivalent to a force. It is what causes an object to rotate. Any force applied to an object where the line of action does not pass through the pivot. Okay, now if we don't have a pivot, the object is going to rotate about its center of mass. Then the center of mass would take the role of the pivot if the object is freely moving. Now, any force that's applied to an object where the line of action does not pass through the pivot will result in rotation. Again, as we mentioned, the torque is force times lever arm. Now, for example, this force F here acting on this piece of metal, the line of action is the dashed line in blue. So this is my lever arm, what's written here as R perpendicular. And as we mentioned, the torque can cause either clockwise or counterclockwise rotation. An alternative way of thinking of the torque in this particular case is to think of our force as two components, Ft and Fr. The line of action of Fr passes by the pivot, so Fr does not result in rotation. However, Ft, its line of action is perpendicular to the rod here. And the distance separating that dashed line for Ft from the pivot is just R. So the torque is also equal to Ft times R.